Hello everyone, my name is Amish Shukla and today I will be presenting on the topic of high temperature superconductivity in hydrogen rich materials. So let's start. So the first question is why we need superconductivity. So we have systems where electrical energy loss during transmission remains a major limitation in modern technology. Even with advanced materials, resistive losses cannot be completely eliminated. Now, imagine a system where electrical resistance becomes exactly zero. This is the phenomenon of superconductivity. So in this presentation, I will explore how recent developments in hydrogen-rich materials under extreme conditions have pushed superconductivity to a remarkably high temperatures, bringing us closer to the possibility of room temperature superconductivity. So let's talk what is superconductivity. Superconductivity is a quantum mechanical phenomenon in which a material exhibits zero electrical resistance below a critical temperature denoted by Tc. In addition, superconductors exhibit perfect diamagnetism, the Meissner effect, where magnetic fields are expelled from the interior of the material. These properties enable superconductors for important applications such as magnetic levitation and medical imaging technologies. However, most of the superconductors require extremely low temperatures, which significantly limits their practical use. Now, let we understand what superconductivity is. Let us look at the theoretical background behind it. So, the microscopic understanding of superconductivity is provided by the BCS theory, where electrons form bound states known as Cooper pairs due to electron-phonon interactions. The transition temperature Tc depends on several key factors, that is the frequency of lattice vibrations, the strength of electron-phonon coupling, the electronic density of states, etc. Interestingly, there is no strict theoretical upper limit on Tc within this framework. This suggests that if these parameters can be optimized, superconductivity at much higher temperatures is possible. And hydrogen is particularly important in this context because of its low atomic mass that leads to very high phonon frequency, and it enhances electron-phonon interaction. Theoretical studies predict that metallic hydrogen could exhibit superconductivity near room temperatures under extremely high pressure. So this motivates the search for suitable materials. Instead of pure hydrogen, hydrogen-rich compounds known as hydrides provide a practical approach. Among these, sulfur hydride becomes particularly important because it can mimic the properties of metallic hydrogen under pressure. Under high pressure, around 90 to 100 gigapascal, sulfur hydride undergoes a transition from a semi-conducting state to a metallic state. This transition significantly enhances the density of states and electron-phonon coupling. Upon cooling, the electrical resistance drops sharply, indicating superconductivity. The transition temperature reaches around 200 C Kelvin, which is exceptionally high and makes a major breakthrough. But for this to happen, metallization is essential. At normal conditions, sulfur hydride behaves as an insulator or semiconductor due to the presence of an energy band gap between the valence and conduction bands. However, when high pressure is applied, the interatomic distance decreases significantly. This leads to stronger overlapping between electronic orbitals. As a result, the energy bands broaden and the band gap gradually reduces. At sufficiently high pressure, the band gap closes completely and the material undergoes a transition from a metallic state. In this metallic phase, electrons become delocalized and can move freely across the lattice. This is essential for superconductivity because copper pairing requires the presence of free electrons near the Fermi level. Thus, pressure effectively modifies the electronic structure and drives the system from an insulating state to a superconducting metallic state. Now let us see that how this is achieved experimentally. To achieve such extreme pressures, a device known as a diamond anvil cell is used. In this setup, a very small sample of sulfur hydride is placed between the flat tips of two opposing diamonds. By applying force, pressure exceeding 100 gigapascals can be generated, which are comparable to the pressures found deep inside the earth. Diamonds are used not only because of their exceptional hardness but also because they are transparent, allowing optical and spectroscopic measurements to be performed during the experiment. The sample is typically loaded along with a pressure transmitting medium to ensure uniform compression. Pressure calibration is often carried out using standard techniques such as Ruby fluorescence. Once the desired pressure is achieved, the sample is gradually cooled to observe the superconducting transition. The primary measurement used is the four-probe resistance method. In this technique, four electrical contacts are attached to the sample, two for passing current and two for measuring voltage. This configuration eliminates contact resistance and allows precise measurement of intrinsic electrical resistance. And as the temperature is lowered, the resistance is continuously monitored. A sudden drop to zero indicates the onset of superconductivity. In addition to electrical measurements, magnetic field dependence is also studied. Applying an external magnetic field surpasses superconductivity, which helps confirm the presence of Cooper pairing. Spectroscopic techniques such as Raman spectroscopy are also used to probe structural changes and identify possible phase transformations under pressure. Together, these experimental methods provide strong and consistent evidence for superconductivity in sulfur hydride under high pressures. At high pressure, sulfur hydride transforms into a metallic phase. Upon cooling, the electrical resistance drops abruptly to zero, which is a clear signature of superconductivity. The transition temperature requires around 200 C Kelvin, which is significantly higher than the most conventional superconductors. A strong isotope effect is observed, meaning that the replacing hydrogen with a heavier isotope reduces the transition temperature. This confirms that phonons play a central role in the pairing mechanism. The superconducting state is also suppressed by magnetic fields, which is consistent with the breaking of Cooper pairs. Together, these results confirm that superconductivity in this system follows the conventional PCS mechanism. However, despite these promising results, there are some limitations also. The main limitation is the requirement of extremely high pressure, around 100 gigapascal, which is not practical for real world applications. And such pressures are comparable to those found deep inside planetary interiors. The superconducting state is also observed only in a small sample volumes, making scalability difficult. In addition, pressure is not an easily controllable parameter. In practical devices, unlike temperatures or magnetic fields, these factors limit the immediate technological applicability of such systems. To understand its importance, let us compare it with other superconductors. Cuprate superconductors were the first materials to achieve high transition temperatures, reaching values around 164 Kelvin. However, their mechanism is still not fully understood and is often described as unconventional, involving strong electron correlations rather than simple electron-phonon interaction. In contrast, hydride superconductors follow the conventional BCS mechanism, where superconductivity arises due to electron-phonon coupling. Despite this, hydrides achieve even higher transition temperatures exceeding 200 Kelvin. This is significant because it shows that very high transition temperatures do not necessarily require exotic or unknown mechanisms. Instead, they can be achieved within a well-established theoretical framework by optimizing material properties such as phonon frequency and coupling strength. Even with this understanding, some important questions remain. Despite the experimental success, several important questions remain unresolved. One major issue is the exact structure of the superconducting phase under high pressure. It is widely believed that H3S forms and is responsible for superconductivity, but direct structural confirmation under such extreme conditions is challenging. There are also ongoing efforts to accurately match experimental observations with theoretical predictions, particularly regarding the strength of electron-phonon coupling. Another important concern is the role of pressure itself. While high pressure enables superconductivity, it also limits practical applications. This leads to a fundamental question whether such high transition temperatures can be achieved without relying on extreme pressure Resolving these issues is essential for both theoretical understanding and practical progress. So, these challenges naturally guide future research direction. So, the discovery of high temperature superconductivity in hydrides has now opened new directions in condensed matter physics. The primary goal now is to identify materials that can exhibit similar superconducting behavior at low pressures or even at ambient conditions. One promising approach is the use of computational methods such as first principles calculations to predict new superconducting materials before experimental synthesis. In addition, exploring different hydrogen-rich compounds and tuning their composition may help achieve better stability and higher transition temperatures. If these challenges are overcome, it could lead to revolutionary applications in energy, transmission, magnetic technologies, and electronic devices. Thus, the field remains an active and rapidly evolving area of research. In conclusion, hydrogen-rich materials demonstrate that very high transition temperatures can be achieved within a conventional BCS framework. The discovery of superconductivity in sulfur hydride at around 200 C Kelvin represents a major breakthrough, as it challenges the long-standing belief that extremely high temperatures require conventional mechanisms. This work shows that by optimizing parameters such as phonon frequency and electron-phonon coupling, it is possible to significantly enhance the transition temperature. At the same time, the requirement of extremely high pressure highlights the gap between fundamental discovery and practical application. Therefore, the key challenge moving forward is to achieve similar superconducting behavior at low pressure or even at ambient conditions. This can be realized it without a transformative impact on energy transmission, electronics, and magnetic technologies. Thus, this research not only deepens our understanding of superconductivity but also brings us closer to the ultimate goal of room temperature superconductivity. Thank you.